Hello. In the previous lecture, we defined the quotient ring and we proved the first isomorphism theorem. And we were in the middle of proving that the quotient ring of the ring of polynomials with coefficients in Q, rational numbers, quotient out by the ideal generated by x squared minus 2 is isomorphic to Q joint root 2. Moreover, Q joint root 2 consists of elements of the form a sub 0 plus a sub 1 root 2 linear combinations of 1 and root 2. So we were in the middle of the proof of this statement. We had already started the first step and we were in the middle of the second step. Let me quickly recall how we approached it. The point is that whenever we have an isomorphism where on one side we have a quotient ring, it's often easier to avoid the quotient ring and focus on the numerator and create and define a ring homomorphism from the numerator to a ring that contains the other side. So in this case, we go to complex numbers. But our goal is to define this ring homomorphism in a way that the image of this ring homomorphism would be the other side, and hopefully the kernel would be the denominator. Okay, so that's the initial step, that's the first step. In this case, we already know that the image, which is Q square bracket root 2, is nothing but the evaluation map, evaluation at the number root 2. So we start with the evaluation map from the ring of polynomials with coefficients inside Q to complex numbers. And again, as we have discussed, we already know that the image of this map is nothing but, this is in fact how we define Q joint root 2. And that is nothing but the values that polynomials take at root 2, polynomials with coefficients inside rational numbers. Okay, so and what does the first isomorphism theorem tell us? It says that the factor ring of the ring of polynomials with coefficients inside Q modeled by the kernel of the evaluation map is isomorphic to the image. Okay, so far we are in good path in a sense that this side is exactly what we wanted, and the other side is a quotient ring of Q bracket X. Now, what else do we need? We need to show that the kernel of this map is indeed the ideal generated by x squared minus 2. It's the principal ideal generated by x squared minus 2. That again means that consists of polynomials that are multiple of x squared minus 2. But what is the kernel of the evaluation map? Again, we have already discussed and we can do it again. The point is that a polynomial belongs to the kernel of the evaluation map precisely when root 2 is a 0 of that polynomial. So kernel of this ring homomorphism consists of those polynomials with rational coefficients that has root 2 as a 0. So the first thing that we are going to do, I mean, after setting up this this picture using the first isomorphism theorem, is to understand the kernel. So we want to show that kernel, those polynomials that have root 2 as a 0, are precisely multiples of x squared minus 2. So that's our goal. The first thing that we notice is I mean, in fact, this is how we define root 2, is that root 2 is a 0 of the polynomial x squared minus 2. In fact, when we plug it in, we get that it is root 2 squared minus 2, and root 2, the way that that's defined, is a number whose square is 2. So therefore, we end up getting 0, and that means that root 2 is indeed a 0 of x squared minus 2. That means x squared minus 2 is an element of the kernel of the evaluation at root 2. And therefore, the ideal the multiples of x squared minus 2 or the ideal generated by x squared minus 2 is a subset of the kernel. Okay, so far we showed one direction of this inclusion. Now I want to show the other way around. So I pick an element inside the kernel and I want to show that it is a multiple of x squared minus 2. So in order to show something is a multiple of x squared minus 2, you have to divide it by x squared minus 2 and show that the remainder is 0. Okay, so we divide x squared minus 2. We divide p of x, this element of the kernel, by x squared minus 2, and let's assume that the remainder is some polynomial. So we have a quotient, we use long division, we have a quotient, q, and a remainder, let's call that remainder r. So we have a quotient and a remainder r, and our goal is to show that r is indeed 0. Okay, so what does being a quotient and remainder mean? It means that when I use the quotient multiplied by x squared minus 2 and add the remainder, I get back the polynomial that I started with. So my polynomial p is the quotient times x squared minus 2 plus the remainder. And what does remainder, being a remainder, mean? It means that the degree of the remainder is strictly less than the degree of x squared minus 2. But notice, the degree of x squared minus 2 is precisely 2. So degree of r is either, it cannot be more than 2. So it is a linear function, it's a linear polynomial. So it is a sub 0 plus a sub 1x for some a sub 0 and a sub 1. Both of them can be 0, one of them can be 0. But we don't have any term of larger degree. So now we have a fairly good understanding of what r is, but I want to show that r is 0. So let's evaluate both sides of this. I'm going to plug in or substitute root 2 for x. Now, I do know, as part of the assumption, that p is in the kernel of the evaluation map, and therefore when I plug in root 2, I end up getting 0. When I plug in root 2 into x squared minus 2, and I substitute root 2 for x, I get 0 as well. So this is also 0. So we get this equality that 0 is a sub 0 plus root 2 times a sub 1. But that means that both a sub 0 and a sub 1 should be 0. Let's make it precise. Why is that the case? If a sub 1 is not 0, then I can actually divide out by a sub 1 in rational numbers. And I deduce that root 2 is indeed a rational number. But we do know that root 2 is irrational. That gives us a contradiction. So a sub 1 is 0. But if a sub 1 is 0, if I go back to this equality, I plug in a sub 1 equal to 0, and I deduce that a sub 0 is also 0. And therefore, we get that both a sub 1 and a sub 0 are 0. And that means my remainder is 0. That's exactly what we wanted to show. That means the polynomial p, which was in the kernel, an arbitrary polynomial in the kernel, is definitely a multiple of x squared minus 2, which means it is in the principal ideal generated by x squared minus 2. We had discussed that this principal ideal is a subset of the kernel. Now we show that every element of the kernel belongs to this principal ideal. Therefore, kernel is precisely this principal ideal. Okay, so far so good. This means that if we use, and by using step 1 and the first isomorphism theorem, we have that q bracket x mod out by the kernel, which is precisely the principal ideal generated by s squared minus 2, is isomorphic to q bracket square bracket root 2. Okay, so the only remaining part is to show that the ring generated by root 2 and Q consists of elements of the form a sub 0 plus a sub 1 root 2, where a sub 0 and a sub 1 belong to Q. Again, let's try to understand the subtlety. By the definition of Q bracket root 2, it consists of polynomials evaluated at root 2. So these polynomials can have arbitrary large degree. But if you think about it here, we are just given polynomials of degree at most 1. And we are evaluating those polynomials at root 2. And we are saying the rest of the polynomials, when I evaluate them, can be rearranged, recompute, and end up getting actually a polynomial of degree 1 with the same value at root 2. Okay, so this is step. This is what we want to do. So we pick an arbitrary element of this side. That means I'm picking an arbitrary polynomial f. I'm evaluating it at root 2. Okay, so that's my polynomial f. I'm evaluating it at root 2. Now, the key tool is again long division. So we again use long division in order to answer this question. So how do we do it? Again, we divide our polynomial by x squared minus 2. And then we get a quotient and a remainder. Why did I choose x squared minus 2? This is the generator of the kernel. That's why we have chosen x squared minus 2. Okay, so this means I take this polynomial, I get a quotient, and I get a remainder when I divide it by x squared minus 2. And this is chosen because this is a generator. This is a generator of the kernel. Okay, so in future examples, this will be replaced by a generator of the kernel. Okay, so now, again, because R is the remainder, that means the degree of R cannot be more, it's definitely less than 2, cannot be more than 1. Again, that means that it is a linear function. This means it is of the form a sub 0 plus a sub 1x for some rational numbers, a sub 0 and a sub 1. Okay, now let's plug in root 2. Let's substitute root 2 for x. And then we get, again here in this equation 1, I'm going to plug in root 2. And then I get that it is f of root 2, which is the value I'm interested in. This is an arbitrary element of the image, is going to be, this term is going to be entirely 0 because root 2 is a 0 of the factor x squared minus 2. So no matter what the quotient is, the product will be 0. So this means the value of f at root 2 is the same as the value of the remainder at root 2, which means, again, f of root 2 is a sub 0 plus a sub 1 root 2 for some a sub 0 and a sub 1. And that's exactly what we wanted to show. This implies that the image is indeed a subring of the set of elements of the form a sub 0 plus a sub 1 root 2, where a sub 0 and a sub 1 are rational numbers. Now, to show the other direction, it's rather easy. I've already pointed out that every element in the set a sub 0 plus a sub 1 root 2 is in fact evaluating this linear polynomial, okay, or maybe a zero polynomial or constant polynomial at root 2. So definitely it is in the image of the evaluation map. So altogether, we have shown that Q bracket X, the quotient ring of Q bracket X by the principal ideal generated by x squared minus 2 is precisely the ring generated by Q and root 2, and the subring generated by Q and root 2 consists of elements of the form a sub 0 plus a sub 1 root 2. So we will be using many techniques, different techniques, in order to generalize this statement and understand the ring structure of Q joint with some zero of a polynomial. And we will be using, again, evaluation maps. We will be using various irreducibility criteria, understanding of ideals of Q bracket X. What else? Understanding of maximal ideals. What are maximal ideals? And long division in general, in more generality, in order to understand this kind of questions. Okay, so, but let's go back in the previous question and think about it closely. We see that long division had been used in at least 2 places and played an important role in the proof. So we wonder if we have long division for more general ring of polynomials. So let's study ring of polynomials for an arbitrary ring in more details with more formal definitions. Okay, so again, we want to develop long division as general as possible and try to use it for other rings besides a ring of rational numbers. Okay, so let's start with understanding degree of polynomials for an arbitrary ring A. So suppose A is a unital commutative ring, and then I consider a polynomial in ring of polynomials with coefficients inside A. Then there are 2 cases, either F, this polynomial is the zero polynomial, or a non-zero polynomial. Let's start with a non-zero polynomial. If it is non-zero, that means I can write it as a constant a sub 0, then a sub 1 times x, then a sub 2 times x squared, and so on, till I get to the largest degree possible in F. So we get to the term a sub n x to the n, where a sub n is not 0. Okay, so because I assume the polynomial is not 0, at some point I get a non-zero term, and beyond that all the terms are 0. So I get the largest degree, the largest degree of xi's, power of xi's. In that case, the term a sub nx to the n is called the leading term. So a sub n x to the n is called the leading term of the polynomial f. And I'm going to denote this by LD for leading of f. So we denote this guy by LD, the leading term of f. Okay. The leading term has 2 information in itself. So one of them is the coefficient. We call that one the leading coefficient. So this is called the leading coefficient. This is the leading term. The other content that it has is the power. And the power is called the degree, the exponent. Okay, so what about 0? We take the following convention and we say that if I give you the 0 polynomial, then its degree is negative infinity. Okay, so the degree of the 0 polynomial is negative infinity. So that's, again, a convention that we are using in this course, that the degree of the 0 polynomial, we call it to be negative infinity. Okay, so if the polynomial is not 0, then if the polynomial is not 0, then we say that the degree is the largest non-zero, the largest exponent that has a non-zero coefficient. That term is called the leading coefficient. That term is called the leading term, and that coefficient is called the leading coefficient. So let's see one example. Let's look at the ring Z sub 6 bracket X. And the question is, what is the degree of the product of these two polynomials? 2x plus 1 times 3x squared plus 1. Okay, so how can we find the degree? Let's distribute and find out what the product is. So as we distribute, we get that it's the first term would be 2x times 3x squared, which is 2 times 3, x to power 3. Then I get 2x, then I get 3x squared, and then I get 1. But notice 2 times 3 is 0 in Z sub 6, which means this term disappears. And I get, if I order it in terms of the exponent of x, I get that I have 3x squared plus 2x plus 1. The term 3x squared is called the leading term. It has two information in it: the coefficient, which we call the leading coefficient, and the exponent that we call the degree. So the degree of this product is actually 2. Now, notice that degree of 2x plus 1 is 1. The leading coefficient is 2, the degree is 1. And the degree of 3x squared plus 1 is 2. So in this example, we see that the degree of product of two polynomials is not necessarily summation of the degrees in general. So in this example, this formula that we used in calculus, and it's pretty useful, fails. Okay, so but let's try to understand why did it fail. So the key point is that here 2 times 3, that was supposed to be our new leading coefficient, is actually 0. So all of a sudden we are losing our expected leading coefficient. Then we need to go to the next best candidate. So why did it happen? The point is that 2 times 3 is 0, but neither 2 nor 3 are 0. We call such elements zero divisors. So if we don't have zero divisors, this phenomena cannot happen. And when don't we have zero divisors? When we are working with integral domains. So then it brings us to the next one. But let's also again point out that the key thing is that if I know the product of leading coefficients is not 0, then I am fine. So later we will use this fact. For instance, if one of the leading coefficients is a unit, then for sure their product cannot be 0. A unit times a non-zero element is never 0. Or in general, a non-zero, an element that's not a zero divisor times another one is never 0. Times a non-zero element is never 0. A unit is not a zero divisor. Therefore, a unit times a non-zero element is always non-zero. So if I know the leading coefficient of one of the polynomials, f or g, is a unit, then this phenomena cannot happen. Okay, but let's make it precise, go slowly, understand what we are doing. As I've explained, this equation failed because z sub 6 has 0 divisors. But if I start with an integral domain, then we want to show that we do have the degree of the product is summation of degrees. Moreover, the leading term of the product is always product of the leading terms, leading term of f times leading term of g. Let's also use this convention that the leading term of the 0 polynomial, we define it to be 0. So we just define this. Okay, so in order to show this equality, I'm going to split it in 2 cases. So either one of them is 0 or neither of them are 0. So let's start with the easier case where one of them is 0. So either f is 0 or g is 0. That's my case 1. In that case, their product is definitely 0. And that means their leading coefficient is definitely 0. But notice, if f is 0, then its leading coefficient is 0. If g is 0, its leading coefficient is 0. So definitely their product is going to be 0, and I get this desired equality. Okay, how about the degree? Now, both of them are 0. I mean, the leading terms are 0. I mean, the product is 0. So now, because fg is 0, then the degree by definition is negative infinity. Now, if f is 0, its degree is negative infinity. Negative infinity plus every integer, we use this convention that we set it to be negative infinity. And negative infinity plus negative infinity, we also use this convention and define it to be negative infinity. So in either case, we get that this summation is also negative infinity. This is a convention. I mean, of course, negative infinity is not a number, so it doesn't make sense to add it with any other number or by itself, but it's a reasonable convention, right? So negative infinity plus some integer should be still negative infinity, and negative infinity plus negative infinity should be negative infinity. So it does make sense to use this kind of convention. Okay, so in any case, we are done with case 1. Now let's assume that neither f nor g are 0. That means what? That means we have a non-zero leading term. That means f of x is a non-zero leading term, a sub nx to the n, plus terms that have degrees strictly less than n. And because g is not 0, again, I can do the same for g, and then that means I can write it as it's a non-zero leading term, b sub mx to the m, plus terms that have a strict degree strictly less than m. Now, when I multiply f by g, I use distribution law, then the leading term of f is going to multiply, we are going to multiply the leading term of f by leading term of g, and I end up getting a sub n, b sub m, x to power m plus n, and the other terms will have degree definitely strictly less than mn. So this means if a sub n, b sub m is not 0, then this would be my new leading term. So this is a leading term. This is the leading term of the product. Assuming that the coefficient a sub n, b sub m is not 0. Okay, so now the question is it not 0? If it was 0, because we do not have 0 divisors, one of the either a sub n or b sub n should be 0. But neither of them are 0, because a sub n is the leading coefficient of f and b sub m is the leading coefficient of g. We assume that f and g are non-zero, so a sub n and b sub m are not 0. So altogether, we deduce that this coefficient is indeed, this coefficient is indeed non-zero. And therefore, this is my leading term, and so the degree of this polynomial is nothing but n plus m. N was degree of f, and m is degree of g, so we get the desired equality. And we also observe that the leading coefficient of fg is the product of leading coefficients of f and g. Okay, so when D is an integral domain, then things go smoothly, and it's similar to what we already had for complex numbers, real numbers. The degree of product is the same as summation of degrees. It's a crucial equality. We are going to use it again and again. For instance, let's see how we can use this to understand that if D is an integral domain, then so is the ring of polynomials with coefficients inside D. So as you will see, the proof is rather easy, but it's going to have striking applications in congruence arithmetic. Okay, so let's see why this is the case. So suppose D is an integral domain, and I want to show that the ring of polynomials with coefficients inside D is also an integral domain. Okay, so we already know that D is a unital commutative ring. That immediately implies that the ring of polynomials with coefficients inside D is also a unital commutative ring. We also know, because D is an integral domain, is a non-trivial ring. It means it has two elements at least. And so the ring of polynomials with coefficients inside D, it has a copy of D in it, just the constant polynomials. And therefore that one is also non-trivial. Okay, so the only thing that we need to focus on is to show that D bracket X does not have a zero divisor. So suppose product of two polynomials is actually 0, and I want to show that one of them should be 0. I'm going to apply the degree function to both sides. Knowing that f times g is 0 implies that the degree of the product is actually negative infinity. But we do know that degree of product is summation of degrees. So this implies that degree of f plus degree of g is negative infinity. But this means degree of f and degree of g cannot be integers, both of them at the same time. One of them should be negative infinity, because when I add two integers, I will end up getting an integer. I do not get negative infinity all of a sudden. So this means either degree of f or degree of g should be negative infinity. But that's the same as saying that either f is 0 or g is 0. So in any case, that means that in D bracket X, we do not have zero divisors. And altogether, we deduce that D bracket X is indeed an integral domain. Let's see more applications of this simple equation. The degree of product is summation of degrees. What is this application? Is to understand what are the units of the ring of polynomials with coefficients inside D. In fact, you've seen a similar question previously, that if I look at polynomials with coefficients inside Q, then the ring of units, the group of units consists of units of Q, non-zero constant polynomials. So in the case of an integral domain, the units of the ring of polynomials with coefficients inside D would be precisely units inside D. So constant polynomials and units inside D. Not any constant polynomial, but rather units inside D. Okay, so let's see why this is the case. Let's observe that if I start with a unit inside the constant polynomials, then it is a unit in the ring of polynomials as well, because if U is a unit in D, then I have an inverse for U in D. I have a multiplicative inverse. But D lives inside the ring of polynomials. And therefore, U inverse is also inside D bracket X. That implies that U is a unit inside D bracket X. So this means that the group of units of D is a subgroup of the group of units of the ring of polynomials. So that part was easy. Let's go to the more interesting part. So suppose I give you a polynomial that is a unit inside the ring of polynomials with coefficients inside D. What does that mean? By definition, that means I can find some polynomial inside the same ring such that their product is 1. Now I'm going to apply the degree function to both sides of this equation. The degree of the product, f by g, is the degree of the constant function 1. But degree of the constant function 1, or constant polynomial 1, is indeed 0. So we get that degree of fg is 0. That means degree of f plus degree of g is 0. But notice, this in particular implies that neither can be negative infinity. And so if a polynomial does not have degree negative infinity, it has a non-negative integer degree. So again, degree of a polynomial is either a non-negative integer or it is negative infinity. As soon as we say these polynomials are non-zero polynomials, we immediately deduce that their degree cannot be a negative integer. So this means degree of f and degree of g, both of them are non-negative numbers, but they add up to 0. How can we have that? The only possibility is that both of them have degree 0. A polynomial of degree 0 is a constant polynomial. So this means f and g, both of them, are elements of D. So f is some constant a and g is a constant b. And fg was 1. This means ab is 1. In particular, that implies that a is a unit inside the ring D. But a was precisely the polynomial f. So altogether, we deduced that every unit of the ring of polynomials with coefficients inside an integral domain is a unit in the integral domain. So altogether, we deduce the result. Okay, so let me point out that this condition of being integral domain is extremely crucial here. And you will see more examples of this type in your discussion and problem session. Just think about the following example, for instance. So show that 1 plus 2x is a unit in Z4x. And it's kind of a result that you have already seen. Notice that 2x is nilpotent inside this ring. And therefore, you have seen that if a is nilpotent, then 1 plus a is a unit. Now, 2x is nilpotent because when I square it, I get 0. So using this, you get that 1 plus 2x is a unit inside this ring. So you see, having the integral domain condition is kind of crucial in the above corollary. As you can see here, 1 plus 2x is not a constant polynomial, but still it's a unit inside this ring. Okay, so now let's go to the long division as we have promised. Okay, so what is long division? The statement is following, that if I give you a unital commutative ring, then whenever I give you two polynomials, f and g, we can divide f by g, get a quotient and a remainder. We cannot do it in general. Let's remind ourselves how the process works. So the process was like this. I mean, we have this g, we write it over here. So we have the g, we write it over here. And then we divide it by f. So the first thing that we do is the following. We look at this term. If the degree of this guy is less than this one, we are done. That's our remainder. If it's not, we are going to match them. What do I mean by match them? So this means I'm going to multiply this by something. I'm going to multiply bm x to the m by some term, a single term, to match a sub nx to the n, because I'm going to multiply and then subtract to get a polynomial of a smaller degree and then try to continue this process. So this means I have to match the powers of x first. So that's why we needed this assumption that n should be at least m, so that I can write down x to power n minus m, and that gives me a polynomial. N minus m is non-negative. So far I've matched the x part. Now I want to match the coefficients. So I'm answering now this linear equation. can I write down A sub n as a multiple of B sub m? So is A sub n a multiple of B sub m? So in general, we've seen that in rings, A sub n equals to B sub m y does not have a solution, but it does have a solution as soon as B sub m is a unit. That's the condition that we are going to impose. That's why we have this condition over here, that B sub m is a unit inside this ring. As soon as the leading coefficient of G, B sub m, is a unit, we can actually go through the long division process that you've seen in your, I don't know, middle school. So again, let's try to go through it. So I'm going to multiply B sub m by something, ending up getting A sub n. Knowing that B sub m is a unit, I can multiply by B sub m inverse, and I get A sub n, B sub m inverse. So I multiply by this. This way I'm going to match the leading terms. I subtract it out. I get a polynomial of a smaller degree and repeat this process. So I repeat this process. This is the essence of the proof of this long division. Okay, now let's go back to the statement and we are going to make it precise. So again, I'm given two polynomials with coefficients inside a unital commutative ring. My assumption is that the leading coefficient of G is a unit. Then there is a unique pair, there are unique Q and R. Q we call a quotient or the quotient because it's unique, we have to prove though. And R that we call the remainder, such that the following properties hold. So what are the properties? So as before, saying that it's quotient and remainder, it means that when I multiply G by the quotient, so I have these two players, F and G, I'm dividing F by G, knowing that, saying that Q is the quotient and R is the remainder means G times Q plus the remaining part is my F. And when I say it's remainder, that means the degree of R should be strictly less than degree of G. If it's still at least degree of G, then I should be able to continue the process of long division. So I stop only when degree of R is strictly less than degree of G. Okay, so that's the statement of long division. Let's prove it. We start by proving the existence first, and then we show the uniqueness later. So what do I mean by that? First, I will show that there are Q and R with these two properties, 1 and 2. Then later I will show that if I give you two pairs with the same properties, if Q1, R1 and Q2, R2, both of them satisfy these two properties, then I need to show that Q1 is indeed Q2 and R1 is indeed R2. Okay, let's start with showing the existence. And as I have indicated, we are going to follow the long division process. But if you remember, in the long division process, I said we are going to get rid of the leading term and then continue like that. In mathematics, whenever you hear this phrase and then we continue like that, means that we are using induction. And here we are going to use induction or strong induction as some, we don't distinguish these two anymore, but in 109 you often distinguish them. So we use a strong induction on the degree of F. Notice that if degree of F is strictly less than degree of G, then there is no need to divide anymore. So you have already reached to the remainder. So if the degree of F is strictly less than degree of G, there is no multiple of G in it. So I can take the quotient to be 0 and the remainder to be the entire f, I mean the f itself. And then if you think about it, because I have assumed degree of f is strictly less than degree of g, I get this property. And because q is 0 and r is f, I get this property. So this means we are done in this case. In this scenario, if degree of f is strictly less than m, which is degree of g, we are done. So next, I'm going to do the process. As I have indicated, I want to match the leading term of f and then multiply g by this auxiliary term subtracting that. So what does that mean? Again, we are given this leading term of f, which is a sub n x to the n. We are going to write it as leading term of g times something. And we can solve this, we can find such a thing, because first of all, we assumed n is at least m, otherwise we were done by case 1. And more importantly, b sub n, the leading coefficient of g, is a unit. Therefore, we can create this term, multiply it, and get the leading term of f. So now what? This means when I consider f, so this is the long division, right? So this means this guy times g, this term that we found times g, I have to subtract f by this product. And when I do so, I'm getting rid of the leading term of f. So I end up getting terms that have degree strictly less than n. So this means the difference would have degree strictly less than n. Now that the degree of this polynomial is strictly less than n, I can use the strong induction hypothesis and divide out this binomial by g. So I get a quotient and a remainder for dividing this polynomial, this new polynomial, by g. So when I divide it out, I get a quotient q bar and I get a remainder r. Again, what does that mean? This means these two polynomials satisfy this equality and this one. Okay, now I want to use these two new polynomials, q bar and r, in order to get a quotient and remainder for f dividing by g. Now it's rather easy because now I can bring this term to the other side. As I do so and factor out g's, both of them have multiple, both of them are multiples of g. I can factor out g. I end up getting this term that we call q times g plus r. You see, f is going to be q times g plus r. And degree of r is strictly less than degree of g. And that finishes the proof. That shows me that we have such q and r using strong induction. And this is exactly how we do long division, how you have learned to do long division. But why do I have a uniqueness? So what does that mean again? That means that if I start with q1r1 and q2r2, if both of them satisfy these conditions, why do I know that they are the same pairs? So this means I have this equality and I have these inequalities, and I want to show that q1 is the same as q2. Let's manipulate these inequalities, bring this guy to the other side and so on. That way we end up getting that g times this difference is the same as this difference. Now, because r sub i's have degree less than degree of g, their difference is going to have degree strictly less than degree of g. Now you see, here I have a multiple of g, then I have, and then I'm deducing that this multiple of g, which is r1 minus r2, has degree strictly less than degree of G. This cannot happen. If we had the equality that the degree of product is summation of degrees, then we could not have this. But here it's an arbitrary unital ring, so you have to pay a bit more attention. And the reason that we still have this, the fact that degree of product is going to be summation of degrees for this particular case, is because the leading coefficient of G is a unit. So more precisely, if I assume Q1 is not Q2, then when I multiply it out by G, then the candidate leading term would be B sub m times C sub k times x to power m plus k. This candidate leading term would be the precise leading term as soon as this coefficient is not 0. But how do I know that it's not 0? It is not 0 because B sub m is a unit. B sub m is a unit and C sub k is not 0, therefore their product cannot be 0. This implies that the degree of this product is precisely summation of these degrees. In particular, it cannot be smaller than degree of G. But that's a contradiction because of this. It's supposed to be smaller than degree of G. So we get a contradiction. That means that this cannot happen. That means that Q1 cannot be different from Q2. So Q1 is Q2. When Q1 is Q2, again, I can go back to this equality and deduce that R1 is also R2. And this finishes the proof of long division. Okay, we will be using long division in the next lecture to show factor theorem and generalized factor theorem, and we use them in other examples for now.